So what do you think? Everyone is here that we expect, Renato? Do you think everyone is here that, or are people still coming from lectures or something? Or I saw Juan Carlos. But, okay. Maybe he escaped in time. We've been waiting for 1.5 hours for Juan Carlos, and then he doesn't want to be here. No worries. Yeah, should I start? Okay. So, yeah, this is my second lecture, I guess. And like yesterday, I will mainly discuss, some details of proofs to give you some idea of how you can actually prove things in these last passage percolation context. And you have to realize that the things that I'm telling you, these methods, they're actually used in many of these models. You can see similar arguments. So in that sense, I think it's good to be confronted with them, at least sometimes. And yesterday what we managed to do was to write down a concentration inequality for the length of a path from 0 to RR, and we could show that the deviation from the expectation, the probability that's bigger than U is smaller than something. And then the problem was that here we have this expectation, but what we would like to have is gamma times R, which is the shape function. That would be nice. So the trick will be to show that these two things are actually quite close together. And then you kind of replace this, and then you say, well, for U big enough, this will still be true, and I will be a little bit more detailed later on. So all we need to do is show that this expectation is close. And we already know that just follows from the superadditive ergodic theorem, subadditive, I always forget. So that this expectation is smaller than gamma times R. So we get that for free. And so now we need to lower bound the expectation. And the way we're going to do that is we're going to do a trick. We're going to look at the expectation of L2R, so a point twice as far. And then we're going to see if we can bound this in terms of 2 times the expectation going up to R. And then you make some correction, and maybe that will be good enough. Okay, and what we already saw yesterday is that, let's make a picture. So here's the point 2R. And then here is the line, let's call it h of R, like this. And it's not so hard to see, to prove that this expectation is actually smaller than 2 times the expectation of the maximum of x in this horizontal line of the length from 0 to x, like this. And that's just because, well, there is some point for which this plus this equals the total distance, and then you have a bound, you're bounded by the maximum this way, and the maximum over there as well, and it's symmetric, so you get this factor of 2, and so it should work out. And then, so now we need to do this, which looks a little bit worse because we take the expectation over a maximum of things, and how can we make sure that we have a good bound? Okay, so we start by discretizing. That's somehow a good idea. So I do it like this. You make little blocks. Well, these are not so nice. Okay, well, you get the picture, I hope. And so here on these boxes we have points x of k, and there are 0 up to r of them. And then we have, so these are the points on the diagonal. And then for each box, maybe I should get rid of this. Here we would have like a zk, which is the bottom part of this thing. And what I want to do is we want to take a maximum over all x, but I want to bound it in terms of these finite numbers of xk's and the zk's. And the question is how I'm going to do that. So let's see, there's a path going like this. Yeah? And yeah. So let's call this path, let's call this point here at the bottom, let's call it y. Yeah, and this is the x. And we want to bound L of x in some sense. So what can we do? So we can take the L from 0 to x. And yeah, I'm going to look at the path. So I'm going to write down this is smaller than or equal to the L from 0 to this point here, because this point is always further away. So that's, well, at least for some k, this point is further away. So I'll take zk plus the vector 1, 1. And so there exists a case such this is true. And now I take the longest path to this zk plus 1, 1. Like this. And I can split it up into 2 parts. So here we have the point y, so we go from 0 to y. And then from y to this zk plus 1, 1. And now I'm going to trivially upper bound this, because the y, well, it's smaller than either xk or xk plus 1. So when it's on this side, it's smaller than this point, and when it's on this side, it will be smaller than that point. So in any case, it will be smaller than the maximum of going from 0 to, let's say, xk minus 1 and xk. So that's just this one. This one is smaller than this maximum. And then going from y to this point is also smaller than going from zk to that point. Because zk is smaller than the point y, no matter where it is. So I end up with going from zk to zk 1, 1. Like this. So that's nice, because now I've bounded it in terms of these discrete things. So those are all the lengths up to the xk's, and these are all the differences between zk and zk plus this vector 1. So in other words, we have that the maximum over x in hr of the L of 0x will be smaller. And now I have to do the right thing, do the maximum over, yeah, we do the maximum over the whole thing, so that's fine. So we do the maximum, yeah, over all k of L 0 to xk, and this is k between 0 and r, and then plus another maximum And maybe the z case is one less, maybe not. Yeah, it should be one less, I guess. Doesn't matter. And then the maximum of the L from zk to zk plus 1, 1. So this is nice because this is only a finite number of them. And well, there's also a finite number, but you can imagine that this is only a small jump, right? It's only up to, there's only a box of size 1 that you're finding things in. So this won't hurt us very much. And let's see what we can do with this. So, okay, the conclusion would be that this expectation, the one that we're interested in, is smaller than 2 times the expectation of the maximum over k of L0xk, and then 2 times the expectation of the maximum of the z's. Okay, so what's the next step? We have to, I will erase this now. We'll do slightly crude bounds. The first one is on this. So there are boxes of size, well, basically of size 1. And the difference, of course, is bounded by the total number of Poisson points in that thing. And then you have to take the expectation of this. And because we have exponential moments on the weights, and there's a Poisson number, you can kind of believe me that this is smaller than some constant, I guess, yeah, some c times the log of r. Yeah? This whole thing. Maximum over r things, it won't amount to much. Okay, so that's that part. And then the other one. So what we will do is so this is the maximum of the L, and we can also look at the maximum of the expectations. And then we can kind of look at the maximum of L minus its expectation, and that's nicer because we have a bound on L minus its expectation. And we have a probability bound already. It's here.
So the log is coming because of the sum, right, of all possible.
So there are of these things.
Yes.
So that's why you get a log of r. If you take the maximum of more things, it's bad. Otherwise, it would just be constant. Yeah, so my point was that it would be nicer to have the maximum minus the expectation, minus the maximum of the expectation. Or the maximum of L minus its expectation. That would be nicer. And then we could use this control on the fluctuations. So what I'm going to do, I'm going to look at the maximum over k of the expectation from L to xk. But maybe you can already guess. And so this is the maximum up to these points. These are the points xk, points on the diagonal. So which one will have the maximum expectation? When you have this diagonal, which one will have the maximum expectation? The middle one. The middle one will be, it's because of convexity, and it's easy to show that this is true. So this maximum is actually equal to this expectation, the thing that we want. So that's nice. That's right. So what I'm going to do, so let's rewrite it. Expectation of L from 0 to 2r. Okay, is smaller than, and now I'm going to take the expectation of the maximum over k of L, and then I'm going to take the L from 0 to xk minus its expectation, like this. And then I'm going to add the maximum of whatever I just added. And well, that's just 2 times. So that's just the maximum in the middle point. And then you get a factor 2. So you get 2 times the expectation like this. And then there was this c times log of r. Like this. No? Okay. So now I have like a fluctuation around the expectation. And then we're going to see if we can say something useful about this. Okay. So there's still some work to do, I'm afraid. What we're going to do is we're going to look at an event, A, and it's the event where for all k we have that the fluctuation is bounded. So the L from 0 to xk minus its expectation, like this. This is smaller than, and then I need a constant times the log square, I think. Yeah, constants times the square root of r times the log square of r. So this has to do, so square root of r times log of r, that's here. Square root of r times log of r. So a fluctuation larger than that will have a small probability. And that's why there's a log squared here. And then this c, we will choose it so big that you know, this thing will be good enough. That's the idea. Okay. So what happens is that either the event is true and then the maximum is smaller than this, or the event is false and then we need to do something else. Okay, so let's write it out. Yeah, I use too much Blackboard for some reason. Well, yeah, so let's call this thing, let's call it the m of r, this maximum. And then we see 2 things. So the m of r is, well, either A is true, so we get the indicator of A, and then when A is true you get the bound c times square root r times log r squared. That's one thing. Or it's not true, and then, so then I'm going to be really crude. I'm going to say, okay, you know, L of 0xk is certainly smaller than the L of 0 all the way up to 2r. At this point, 2r is bigger than all of these points, right? So this is certainly smaller than that, and this expectation is bigger than 0, so I'm going to be really crude, and I'm going to say, I multiply this with the L of 0, 2r, 2r, like this. And the reason why I can do this, of course, is that the probability of the complement is really, really small. And so then it doesn't matter that I'm being so crude. Everybody agrees that this is true? Okay, so now we can say something about the expectation. Oh dear. Well, let's erase this. So we need to bound the expectation of MR like this. So there's this indicator function of the set A, but you know it's smaller than 1, so we will just get c times square root times the log r squared. And then there's the expectation of this thing, and then I will use Cauchy-Schwarz and say that this is smaller, the expectation of that thing is smaller than the square root of the probability of the complement times the expectation of L all the way up to 2r. Like this, and of course I need to square this. And I need to, yeah. So this is just Cauchy-Schwarz. Okay, yeah, it's a little bit, you might say, well, this doesn't help very much because this expectation we're trying to bound and now it's coming back, but it doesn't matter, we'll be very, very crude. And we will say that this expectation is probably smaller than some, so let me see, it's the expectation of the square. That's it. So the total length of this, all the way up to 2r, is less than the total number of points inside this thing. So, and that's just a Poisson number. The size is 4r squared. So the total number of points, you get that this is smaller than some constant times r to the 4th, for sure. Yeah, that's just the square of a Poisson variable with expectation of the order r squared. You get this. Okay, so that's easy. And then I have this bound here, this probability, and for that, of course, I use this fact here that we have on the fluctuations, and we can see that this probability, so the probability of the complement, well, the complement means that there should be one of them for which this is not true. Probability, of course, is smaller than the sum. That doesn't happen. And then I use this fluctuation bound here, and I get something like a constant times r times e to the minus some other constant times c times, so this is, let's bet b1, and then I get log r, right? Because this fluctuation is of the order square root r log r squared, so you end up with a log r like this. And then, what do I need to do? Yeah. So now I can increase this c, and I get a very low power of r, which means that this term will be smaller than this term. If you increase c, you get r to the minus c, and even if you multiply with r to the 4th, it doesn't matter. So you get some negative power of r, which means that this will be, we can ignore it. We end up with this term for the expectation. And that should be enough. So what's then the final statement? We would get that this is smaller than 2 times the expectation of all the way up to r, and then I have to add something of the order c times square root of r times log squared of r, and then this log r is smaller than this, so we can put it into the constant, and we would have this for all r, big enough. Oh? And in fact, so together with the fact that we know this, if I divide it by r, this will converge to the gamma. That's because of the Radula Theorem. And here we have this functional inequality. So what I could do is I could divide by 2r, for example. So I divide it by 2r. Then I know this will go to gamma for big R. And here I divide by r as well. And then you can divide by r here. Or 2r. Like this. And then you can see that these terms, when you go from 2r to 4r to 8r to 16r, they become like a summable correction term. And in the end, the conclusion is, this is a calculus lemma, basically, what you're using now. But because of the summability argument, your conclusion is that the expectation of 0RR is in fact also bigger than gamma times r minus maybe some other constant times square root of r times log squared of r. Like this. Yeah, so now we have an upper bound and a lower bound. And so this trick was thought of by Howard and Newman. And in fact, you can use it in many other models to show that you have usually many of the concentration results. They say something about fluctuation around the expectation. You want the expectation to be more or less equal to the shape function, so you need an argument like this. And then you can make sure it works. And of course, so what you do now, you replace this expectation by gamma of r, and you make sure that u doesn't feel this small correction, square root r done log squared r. So the result would be, here I would get gamma of r, and then for all u bigger than some constant, I don't know, b3 I guess, times square root r times the log squared of r, like this. Now, so for u big enough, we would have this fluctuation result. And in fact, what we will do, we will use it for orders r to the power a little bit bigger than 1/2. And that's why we won't have any problems here. So things will work out. Okay, so this is the full fluctuation result. Well, full. You have to realize, so we worked quite hard to get this, but in fact it's pretty lousy, the bound. Because what we would expect the fluctuations to be of order r to the 1/3, and this would allow for fluctuations of higher order than square root of r. And so we're not even close to what it should be. But that's one step further. It's a bit difficult to get. And with this result, this fluctuation result, it's enough to say something about the minimizers and control their fluctuations, and then existence of Boltzmann functions and all that. Yeah, so this is enough for that, even though it's certainly not as strong as we would hope. And we would expect a stronger result here. But, well, for that you need, for example, these exactly solvable models. They can do that. Okay. Okay, so now we have to move on to minimizers and see how they behave. And I'm going to be a little bit less detailed, but still I hope to give you a good flavor of how to prove things for that. Okay. Right. So what are the things we're going to look at? Okay, now suppose we have the positive quadrant, and I can make like a big cone of some angle close to pi over 1/2. I need to stay away from the boundary because there's some pathological things happening. So I need this big thing. And what will be the general idea? So suppose I have a point P, and suppose I have a small square around this, so of size 1 around this point P. Okay. And then I create an angle around this P, and I have a notation for this. So this is a cone, and the axis of the cone goes through P, let's say, and it has a certain angle, and the angle would be of the order P to the minus delta, I think. And delta will be a number, I always forget, I think it needs to be bigger than 1/4 or smaller than 1/4. Let's see how it works. Delta, well, we will fix it later. Okay. So what I'm going to do now, I'm going to look at a set of points. So let's say, let's define R out. And then here there's a little box as well. So, well, I will explain it. R out 0, like this. Of the point P. Those are all the points Q. Such that there exists a point which I call 0 tilde, which is a point very close to 0. So it's in a little square 0, 1 squared. So that's somewhere here. It's close to the origin. And there exists a p tilde, which is close to p, also in a little square around it. Such that p tilde is an element of the path, the longest path, going from 0 tilde all the way up to q. So let's make a little picture. So we have q here. And then this q is an element of this outset of p. If the longest path from q to some point close to the origin, if this longest path crosses this little square, like that. And you consider all q for which this is true. Okay. Now why is this an interesting object? Well, the idea is that with high probability, this outset should be inside this cone. And why would that be true? Well, suppose this is what happens, then we know that the L from 0 tilde to q is actually equal to the L from 0 tilde to p tilde plus L of p tilde to q, like this. Because it's the longest path, so you can just add them up. However, I also know that if I look at the expectation from L from 0 to q, let's say, then this is the shape function. The shape function is strictly convex. Here we're going to use this strict convexity. So it's strictly convex, which means that this length in expectation is actually quite a lot bigger than if you first go to p and then from p to q. So this expectation is actually bigger than going from 0 to p and then from p to q. And in fact, you can make an explicit calculation because we have an explicit shape function. This is not really necessary. If you would have a lower bound on the curvature, you could also do a similar bound like this. But what happens in this case is that this difference is at least of the order norm of p to the power 1 minus 2 delta. And here there's a contradiction. Because in expectation, this is much bigger than the sum of these things, but the actual value is equal. Well, of course, little tildes there, it's technical, you have to be a little bit careful, but they're very close to 0 and p, so it doesn't really make a difference. So the actual value is the same. That means that the difference between this one and its expectation, or this one and its expectation, or this one and its expectation, has to be big, has to be of this order. Is that clear? Otherwise, this cannot work out. So one of the three has to have a rather large fluctuation, but we know that it's not possible to have large fluctuations because of this thing. You cannot differ a lot from the shape function. So that's the key. And in fact, what you need is that 1 minus 2 delta should be bigger than 1/2. So I think that's the same as saying delta is smaller than 1/4. And then the fluctuation is of order well, of order bigger than, way bigger than p to the power 1/2 times log of norm p, like this. So those are these points here. Okay. You need also that q is far away from p, like in the same order. Otherwise it doesn't work. If p is very close, then it's more difficult, but we will, this is for q also of order p away. Okay, so how are we going to use this? So it says here that we have like exponential control. We have an exponentially small probability that in this set there's a q far away from p, which is outside of this cone. And we could make it a little bit more precise in the following way. So you take your point P, like this, and then you make a small cylinder, like this. The length, you take the length of P, and then this width, you take p to the power minus delta, like this, maybe times some constant. And then what we're saying is that if you have a q in the R out of p, then the path from q to the little box around p has to go through the top part, because if it goes through the side, then you get this angle that's too large, like we've seen before. And so in fact, you can prove that this event happens with, well, it doesn't happen with exponentially small probability. So what you can do then is kind of concatenate. So now you start at 2p, and then you make another cylinder which is even longer, like this, and you build up on that. And with using Borel-Cantelli, you can sum them all up, because you have, like a polynomial number of these cylinders, and you have exponential bounds, so the whole thing sums up nicely, and you will know that from some point on this will always happen. You'll always stay inside these cylinders. And these cylinders, they always stay inside one of these cones. So I will write down the final result we get from these considerations. It's the following. So we would have that, I could take the probability. So for all p with norm p bigger than some constant, so you have to be far away from 0, far enough. And also p has to be inside some cone around the diagonal with angle theta, so that's this big cone here. Here you have this big cone, and I can do uniformly for all these p's. I can make this this statement. But you need, you don't want to have p's very, very close to the boundaries. That's why you need this extra cone. So for all these p's, we would have that the probability that R out of p is a subset of the cone centered at p with angle p to the minus delta, this probability is bigger than 1 minus, and then there are some constants, c1 e to the minus c2, and then you get norm p to the power kappa, for some positive kappa. You don't, so this kappa can be quite small now, because you did the thing with the delta, and they have to be delta which is smaller than 1/4, so that's where the kappa comes from. But it's positive and it's enough. right? So now you can sum this, and even if you multiply by powers of p, still you can sum this small probability and there won't be any problem. Okay, so all these outgoing sets, they're part of some small angle, and actually this is called also the delta straightness. And you can go on, well, there's another thing that follows from this consideration. So with probability 1, there exists an m bigger than 0, such that for all p in this kind of large cone, so you have to stay away from the boundary, but for all p, you would have that the outset of p is a subset of the cone circled around, centered around p. Now, so now this is a probability 1 statement, that if you are far enough from of course this m that kind of determines the boundary, it would depend on the realization of the Poisson process. But if you're far enough away, then for all p's in this cone and far enough away, we would have that the outgoing points would be inside this cone. So you can kind of really see that this would imply that if you would have very long minimizers, then these minimizers, they have to be somehow straight. They have to have a certain angle, because otherwise you would end up outside of these cones. And that's not possible. Okay. So this is a concept called delta straightness, and we will write down some consequences of this. So the first thing is what I said is if you would have a semi-infinite geodesic, then it has to be straight. So suppose I have an infinite sequence of points in R2, and they are increasing, and they're what's called a semi-infinite geodesic. So what does it mean it's a geodesic? It means that, so 0 is just the origin, the P1, P2 are Poisson points, and if you go from Pn to Pn, then the longest path between these points is exactly following the points in this sequence. So the whole sequence itself, any subset of it, is the longest path. Okay, so then we want to show that this semi-infinite geodesic has a direction, following from this result. And the idea is as follows, that, well, you can have a couple of things. You can look at the lim-inf of, let's say, Pn second coordinate, Pn first coordinate. So if this is plus infinity, well, then the direction is just going up. And then if the other possibility is that it would go to 0, and then the direction is 0. And if this is not the case, then you can find a point inside the interval 0p or pi over 2 that is like an accumulation point. Either the lim-inf or the lim-sub will be inside of this interval. So let's call it the lim-inf. So lim-inf of this thing is some alpha, some angle inside of this thing. And then the point, of course, is that if there is some subsequence going to alpha, then you can take a faraway p that is more or less on the angle alpha, and then the cone around p will be small. So, so what would we have? Is this would be close to, well, not, I guess, the tangent of alpha. And for some large n, and then for all subsequent n, we would have, and so this is p of n is bigger than m, and then we know that the r out of this pn is a subset of the convex hole, the cone around P with this angle. Now this angle can be small and epsilon for large P, and of course this outgoing set, it contains all the other ones. Pn plus 1, Pn plus 2, etc. They're all an element of this outgoing set. And because the longest path to 0 goes through these points. So that means that all these points have to be inside this cone, which means that their angle should be alpha plus some small epsilon. And this could hold for any epsilon. So in fact, this would imply that the limit exists and equals to, now I guess I'm missing some tangent. Pn2, Pn1 would be equal to the tangent of the same alpha. Yeah? So there can only be one accumulation point, and in fact there will be a limit point of the whole thing. So that's nice. These semi-infinite geodesics, they cannot wander around very much. They would have to follow a straight line. But what would be nicer if we could show that actually there exists a limiting point. I'm sorry, a semi-infinite geodesic in a certain direction. And that's, well, not so easy. You have to do some work with that as well. Okay. So what do we do? I'm going to try and prove the following thing. So suppose I have a sequence yn tn, a fixed sequence, and it goes up to infinity, so like this, and it follows a certain direction. So yn over tn converges to the tangent of alpha. So this is a deterministic thing. I can choose, whatever sequence I like. So here's the direction alpha, and here are these points. Okay, and what I want to do is I want to choose a subsequence of these stats, and then look at the path through 0 of the subsequence, and the claim will be that this will converge to an actual semi-infinite geodesic, and it will have the right direction because, well, they all start at these yns. And so by going through a subsequence, I want to show that this should converge. Okay, so how do I do that? Well, we start by saying that let's make sure that the first point, let's call this x of n. So the first point is already far away. So far away that we have the delta straightness. That would be nice. And okay. So I'm further away than n. I have a point y1 here, and I know so I can make a cone around this point. Right, now I'm a little bit confused, of course. So what do we need? Yeah, what I wanted to say is that all these paths should be in this cone, but now I'm not so sure why that's true. Yes, that's true. Okay. So I'm making a new picture, I'm sorry. This is not so clear. A new picture. Here's my points. Sequence of points going away like that. And maybe I will define these subset of points. I'm going to make a cone around, let's say, the first one. And the claim is that all the paths starting from points further up, they have to stay within this cone. And the reason is that if this path would go outside of the cone, then the delta straightness would be violated for this path. Because there would be a point far away here where it would touch. You could make this point into a cone like this with the same angle. They would not overlap, so this point would not be in this cone, and therefore this path would violate the delta straightness. And we have delta straightness, we have it for all p in this quadrant, except for some small angles, but that's not a problem. Yeah, so if the path would go outside of this thing, then around here it would touch a point which is, well, let's say outside of this interval here. Then you make a cone around this point here, and that's the violation of the delta straightness. Because this point is also further away than m from the origin. So that means that all these paths, they have to go through this line here, let's say. And there are infinitely many of them, because you can start wherever, they all go through this point. So then the key is that you make a box like this, and if the box is long enough, you can show that the path that will pass through here has to pick up a Poisson point in this thing, because otherwise it's not an optimal path. And you cannot skip the Poisson points in this box, because then it would not be optimal, and there have to be Poisson points here simply because these boxes, they are of the same size as the length of the point. So with the Borel-Tantelli argument, you can show that all these boxes contain Poisson points. But of course there are only finitely many Poisson points, so that means that a whole subsequence has to go through, let's say, this Poisson point. And if they go, all of them, all of the subsequence go through this Poisson point, well, then they also go through the same point here, but well, that's not so relevant. In fact, maybe it is relevant to realize that from this point on, all these paths of that subsequence are the same as this path here. Right? They all coalesce, basically. So then you have the subsequence, and then you go to the next one, and you do the same argument here. So again, there will be a whole subsequence going through some Poisson point here, and they will all be the same from that point on. And then you repeat this argument, and what you end up with is a subsequence of the xn, and then you would have one path, because all of them, they belong to the same path, and that path will be your semi-infinite geodesic, and it will have the right angle because, well, it stays inside of these cones all the time. Well, it's also because of the choice of the x-end. So the delta straightness makes sure that if you have a sequence going to infinity, there's a subsequence, and the longest path to 0 from that subsequence converge to a semi-infinite geodesic with the right length. Now you can prove this for the origin, but in fact, if you work with these boxes, you can show that for any p, wherever you are, with probability 1, there will be, for a fixed direction, there will be, well, not even for a fixed direction, doesn't matter, a geodesic in the direction of alpha. So that's the existence. Existence follows from the delta straightness. Okay. Now we have uniqueness also. We should think about that. So how does that work? No. That's also not so straightforward. You really need a clever trick in order to prove this uniqueness of things. Okay. So we fix alpha, some angle, and suppose P is a Poisson point. This is true for any Poisson point. Then the statement is that there exists a unique gamma, which is semi-infinite geodesic, direction alpha, such that P starts at gamma. Oh, well. So we have a Poisson point, we have a direction, and there's one semi-infinite geodesic starting at the Poisson point. And it's unique. Okay. So how do you prove this? So we start by defining an event indexed by alpha, u of alpha, and it's the event that it's not true, that there is no uniqueness. So in this event, there actually there exists a Poisson point, and there exist two of these geodesics, and P, let's say, starts or is an element of both of these geodesics, semi-infinite geodesics. And that direction alpha. Let's call it this. So this would be, for this alpha, things go wrong. And then we define a set of S. So these are all alphas in 0 pi over 2, such that the probability that this happens is bigger than 0. Okay, well, now you have to realize that we had this special transformation, and maybe you remember, so you could map xt to lambda x t over lambda, and then all the longest path they transform with it, and there's no problem. So what this transformation does is that if you have a certain direction alpha, then this transformation changes the direction. So with this transformation you can go from any alpha to any other alpha. That means that this probability is the same for all alpha. It's kind of a trivial statement. In other words, S is either the empty set or it's the full interval. Simply because every angle is equivalent by this transformation. Okay, that's nice. And then the final step is to prove that this S is countable at most. And if it's countable, then it cannot be the entire interval, it has to be the empty set. So for every alpha, this probability is 0, and we would have proven the statement. So let's see how that works. So to prove that it's countable, we're going to use a new idea. We're going to look at triplets P, Q1, Q2. So these are triplets of Poisson points. And we call them a bifurcation triplet if the following is true. So if there exists gamma 1, gamma 2, alpha geodesics, let's call them. They both start at this P. So here we have P, and then from P, one of them goes to Q1, and the other one goes to Q2, and then they follow their own way. So this is gamma 1, and this is gamma 2, and they never come together again. But they follow the same direction alpha. It's clear that they can never come together again because then we know we have unique minimizers. We have to find them like that. We always take the lowest one. So if they would come together, then you would always take the lowest one and the other one would not be a geodesic. So once they split up, they have to stay apart. Okay. And if you have these two geodesics starting at some P, and they're not the same, then they have to split up at some place. So you would get, and that is the P that is here, the place where they split up. And this will be the bifurcation triple. And clearly, if these things would exist, a Poisson point with two of these gammas, then you would also need one of these bifurcation triplets. No? Okay. Now, the key is that each triplet can only be a bifurcation triplet for one alpha. That's the key. So, each triplet, P, Q1, Q2, only for one alpha. So why is that? Well, suppose it's also a bifurcation triplet for some other direction. What would that mean? It means that there are like a gamma 3 and a gamma 4 corresponding to the other direction. And one would go like this. This would be gamma 3. And the other one would go like this and then like that. It would be gamma 4. Now, why would this be a contradiction? Well, the angles are different, so that means that gamma 1 in this picture, otherwise it could also be the other way around, of course. But in this picture, gamma 1 and gamma 4, they would have to cross somewhere. And that's not possible, because then you can show that only the lowest one can be a geodesic, and the other one cannot be a geodesic. So these things, they cannot cross. Once they started together, they have to either stay together or be apart, but they cannot cross. And that's with probability 1 for all of these things. So this picture shows that these triplets, you cannot have them for two different alphas. And then, well, you can kind of guess that then you're done, because so it takes a little bit of effort, but I'm not going into that. You need to build up the argument a little bit more, but heuristically we're basically done because there are only a countable number of these bifurcation triples. And that's why you would have a problem if there would be an uncountable number of alphas, let's say all alphas basically, that would have a positive probability here. Now you would need too many of these bifurcation triples, and that's not possible because there are only countably many. Is that kind of convincing? That cannot happen? You need to make it a little bit more technical, but this is the idea behind it. It's not possible. So there can only be countable many, and that means that in fact there's no alpha for which this has a positive probability. Now I have to state that we fix alpha and then we say with probability 0 there's non-uniqueness in this direction. But it's known that, for example, in the competition interface direction, you can have two geodesics that have the same direction but are not the same. But of course this direction is random. So you first look at the realization and say, oh look, there's this direction here and there I can find two geodesics. So that doesn't contradict this statement. Now, if you fix alpha, then you will not find them. Okay. Now another consequence of this, I have until
10 or something.
Okay, well, so I have plenty of time. Another consequence of this is that in this case, what I did was I took a subsequence of these points xn going to infinity, and for some subsequence I know that the path would converge. Well, the uniqueness implies in fact that the whole sequence has to, all of them have to converge. Because suppose that there's a subsequence of path to 0 that do not converge to the other one, well then in itself there would be a sequence going to infinity, so they would need a subsequence that converges to an alpha geodesic, and that second alpha geodesic cannot coincide with the previous alpha geodesic. And that's a contradiction because there can only be one. Now you should compare this to the fact that if a sequence has only, so if every subsequence has a converging subsequence but it always goes to the same thing, then the whole limit converges. That's similar here. Yeah? Because of uniqueness, there can be only one alpha geodesic, so all subsequences have subsequences going to this thing. That means that the whole sequence in fact converges. So that's a nice statement. As soon as you have a bunch of points going to infinity according to some direction, then you can just take all the longest paths and they will stabilize and will converge to in fact the unique semi-infinite geodesic in that direction. Okay. So now we come to the most difficult part. We have uniqueness, we have existence. For all points there exist in a certain direction, it's unique. What we also want is, well, of course you would say hyperbolicity, but in this case of course we would have coalescence. We need that if you have two semi-infinite geodesic in a direction alpha, we want them to coalesce after some stage, after some time. And the question is, how do you prove that? That's also an effort. Okay, so we're looking at coalescence. Let's first make a remark. So if I start with two semi-infinite geodesics going in the same direction, then only one of two things only two things can happen. The first one is that they will just stay separate. That could happen. We don't know yet. And the other picture is that they would coalesce and then continue together. And the thing that cannot happen is that they cross. This cannot happen, and what was the reason? That's right. Yeah, that's right. And so this would be, well, you have to be a little bit careful because it doesn't have to be a Poisson point, but you can construct a Poisson point and then you would contradict the uniqueness of that from that Poisson point. So there's a little bit of work, but this cannot happen. So that means that if we just look at alpha rays starting at Poisson points, then they would, you would have like coalescence clusters, right? They would cluster together or not, and then they would form some other cluster. So you would get each alpha ray, each alpha geodesic would belong to some cluster, and one can belong to the same one or to a different one. So the whole thing is split up into clusters. And then what we want to show is that in fact there's only one cluster. Right? That will mean that there's coalescence. You cannot have disjoint clusters. That would be the idea. And the first step to prove that is to show that if you have one of these clusters, then it's bounded from below. Yeah. So, coalescence cluster is bounded from below. I'm sorry, it's not bounded. It has to go, so if you start a cluster like this, then there have to be alpha rays coming from further and further away that join into this cluster. Otherwise, so I think this is a bit strange, but like this is better. Otherwise we'll have a contradiction. Okay? So how do we prove this? Well, suppose that they could be bounded from below. That means that there's also a lowest point. A cluster that's bounded from below has a lowest point. And apparently they could exist with positive probability. And then of course because of translation invariance they could appear basically everywhere. So that means that for all, let's say, I and j in Z2, the probability that there exists a lowest cluster point inside I plus 1, well, let's call it ij plus little square, this probability is positive. Because if it would be 0 for all these things, then they couldn't exist, these lowest points. And so the problem is that every little square like this will have a positive probability of kind of starting one of these clusters, going up, and of course there are many of them, right? And in fact we will show that there will be too many and then we will have a contradiction. Because what's the point of these clusters? They have to be disjoint. Every cluster you start at a different point, they cannot coincide because they are different clusters. Right? In different clusters they don't coincide, so they're all different. But they do need to pick up Poisson points, all of them, and there are just not enough of them. So that's the idea. So we start with, let's say, line 0, and then we could look at, so again, I will not be very precise. So here it is the direction, let's say, minus alpha in this way. And I will look at a cone like this. And so this is, let's say, of order n. So here we have order n, and this is of lower order. I think it's square root of n, or even lower, I'm not sure. And then the point is that in this region, there will be order n squared of these little blocks, and a fraction of those, of the order n squared things, will start one of these clusters, because there's a positive probability for them to do so. So a fraction of those will start one of these clusters. So there's clusters starting like this, and there's another one starting like that. And these are these lowest points. So there are very many of them, and they all have the direction alpha, all these things. And now what you do is you kind of show that all these clusters, they have to pick up a Poisson point in this box. They cannot skip the box without picking up any Poisson points. So that's what you use Borel-Cantelli and the Poisson process to show that there are enough of these Poisson points here that you can pick up some weight. And then, but of course, the number of Poisson points here is of the order n to the 3 over 2, and the number of clusters is of the order n squared. Because this area here is of order n squared. And that's a contradiction. Because each of them has to pick up a different Poisson point. They cannot pick up the same one.
Can you say it again? Why the area, why the number of clusters is of order n squared?
So ergodicity says that each of these little squares has a positive probability of inseminating, of starting one of these clusters. And there are n squared of these little squares, and a fraction of those will start this thing. So that's still order n squared. Again, the technicalities you can use, and I don't know, you use some special ergodic theorem for 2 dimensions. I forgot the name now. Lindenham or something? Or do you know?
You just
Yuri?
define the variable n, which is the number of clusters. Then this says that this is n squared, some constant times n squared times this probability.
Yeah, you can.
Blah, blah, blah. And then you have the upper bound, which is n to the
3 over 2, and that will give you.
this probability has to be 0, otherwise you have.
And that's the idea. You can make it a little bit more technical than that, but anyway, the intuition is kind of clear. There are just too many of them in order for them to pick up these things, and then they would have to pass this boundary. That's also not possible for any longest path to cross this boundary without picking up any point. Okay, so this is only one step. So now we know that all of these clusters, they have to be unbounded from below. You have to go down to infinity. Okay. Next step. I think I will just make it before the end of the talk. The next step is to show that, well, suppose there's, with positive probability, there are 2 clusters that do not intersect, so 2 separate clusters. Well, if that happens with positive probability, then it happens somewhere with positive probability, and then you can use ergodic theorem to show that it has positive probability to happen somewhere else, and then it will happen at least 2 times, not just once in the whole plane. So there will be another set of clusters, and you can even make sure that they cross the same line somewhere with positive probability. This will happen. And that means that, so I can now look at this longest path, call this gamma 1, gamma 2, gamma 3, and gamma 4, and now I will have 3 paths that do not cross each other, namely gamma 1, gamma 2, and gamma 4. They cannot cross, because for gamma 4 to cross gamma 2, it would need to cross gamma 3. That's not possible, because these things, they cannot overlap. They could coalesce. Gamma 2 and gamma 3 could coalesce, that's not a problem. But 1, 2, and 4, they have to be separate paths. Now, so with positive probability, these things exist. These 3 things. Okay, that's nice. Then what? Well, again, these 3 paths, they have to be somewhere. So what you can do is you can say, okay, so I have 3 paths somewhere. I will make sure that with positive probability, I will have a small set here, and this will be the start of my middle path. So that's like gamma 2. There will only be one Poisson point here in this little box, and it will start there. And then I have some other boxes that could be quite far away, but I can find distances such that I can determine little boxes like this, and little boxes like this. So, and what I'm saying is that with positive probability, there will be gamma 1, gamma 2, and gamma 3 that will go like this, and like this, like this. Yeah? And you have to imagine that it might be that here there was also points belonging to gamma 2, but I will ignore them and I will look at gamma 2 only starting from this point. So if there would be these points, I'll just ignore them. It doesn't matter. Okay? And what's important is that I have chosen, so these boxes are deterministic. They're deterministic boxes, and I'm saying that with positive probability, these 3 paths will look exactly like this. Well, not exactly, but inside this box, so you have some freedom. And you can imagine this has to be true for some of these boxes, because otherwise they couldn't, they cannot live anywhere, these paths. And what's important is that this final point here is to the left of this point. That's important. Okay, so there's this big box, like this. And I have with positive probability, I will have an event where these 3 paths will happen. And of course also gamma 1, gamma 2, and gamma 3, they do not coalesce. These are these special 3 paths. And what I'm going to do now, the next trick is that I'm going to change the realization that led to this, to these paths. So what I'm going to do is, there could have been some more Poisson points, like this, and I'm going to erase them. So I'm going to say, if this happens with positive probability, then what also happens with positive probability is that I get the same points in the boxes, but no longer these ones. So I will erase them all. And this is a finite box, so you can imagine that indeed this is possible and you still have a positive probability. Because you will only erase a finite number of points, basically. So if some realization has a positive probability that you see this, then another realization also has positive probability, and that realization doesn't have any Poisson points inside this box other than the one that I have denoted. Okay, and how would this help us? Well,
so the intensity of the Poisson points is always finite on this.
well, it's 1, and it's so it doesn't change at all. No. So we always take it the same. So what is the nice part of this? my claim is now that this particular cluster, the gamma 2, it's lower bounded. There cannot be a path that coalesces with gamma 2. So why is that? Well, so a path starting outside of this box, so below here somewhere, that's not possible. Because you see, if the path is to the left of gamma 1, then it can never coalesce with gamma 2. You have a question? No. And if the path is to the right of gamma 3, then it can also not coalesce with gamma 2 anymore. So the only possible way to coalesce with gamma 2 is if you go in between somehow, like this. But you would never do that because, why not? Oh, I think what's important, in fact, is that this last point is over there, to the left of this beginning point. And you can do that by making it longer and longer. What you should imagine is that if you have these three things, then I can just start very far away here, and then this path will have moved to the left. So it's important to have this point, and now you can see why, I think. And so why can't I just slip into the middle? Well, because then I can always either pick up one of these points or pick up one of those points and then continue my path, because here I didn't pick up anything because there are no Poisson points. I removed those Poisson points. So I can always pick up either a Poisson point from this path or from that path, and then I would continue there, but that's not possible because I would have crossing paths. So they don't exist, those geodesics. So I've kind of created a barrier and made sure that this thing now is lower bounded. The cluster belonging to this point, to this path, is lower bounded, and that contradicts the thing we had before that said that there's probability 0 to have a lower bounded cluster. In other words, there cannot be two separate clusters, and therefore there's only one cluster, and all paths must coalesce with probability 1. This is also an idea by this Burton and Keane argument, right? So it's kind of general setting, and it's used quite a lot. But again, like Costa was saying, it's essentially 1 plus 1 dimensional, because you have these blocking paths, and of course in 3 dimensions you cannot block anything with one path, right? So it wouldn't work, and in fact we don't have any good arguments to show that these clusters would coalesce or anything like that. It only works in 2 dimensions. So there are several places in this whole scheme of the proof where it was essential that we used 1 plus 1 dimension. Okay, I think I will stop here for today.
Any questions? Comments? Well, everybody's hungry.
I can imagine.
Okay, so...
Okay. So that's it for today also, right? The last lecture.